Today's lesson is a lot like the last one. We're still integrating by substitution. The only real difference is that in yesterday's lesson, we were generally given substitutions that were u in terms of x. So it might be something like let u equal 1 minus x or something like that. Whereas today we'll be given substitutions where we have x in terms of u. Now, still we want to do the same basic thing. We want to change all of the terms in x into terms in u, and we want to change dx into du, and we'll use the same method to do that. But because we're given a substitution that's x in terms of u, there's quite a lot more situations where we also need to rearrange our substitution and get u in terms of x, and we might need both parts in our integration. Now, when you're rearranging u in terms of x or x in terms of u so that you can use them either way, a couple of things that could crop up. You might get multiple possibilities. Now, if you do, in this course, it shouldn't be a major problem. Later on, if you're studying this sort of thing at a university level, you'll need to understand the nuances of this issue. But for this course, generally, if you stick to positive square roots and stay in the same quadrant as the original variable for any trig questions, you'll be okay. Now, what I mean by that is if you've got something like use the substitution x equals sine of u, then if you're knowing what u is and you're thinking about what x could be and there's multiple answers, clearly we're just going to keep with the simplest answer and stay in the same quadrant. Or if you had something like x equals u squared and then you want to rearrange that so you've got u equals and you're wondering whether to use the positive or the negative square root of x, just go for the positive ones and things should generally work out okay. Now, this first example will probably look a little bit familiar. We've done it twice already. Once when we looked at indefinite integrals, and then again when we looked at definite integrals. And in fact, we've answered this very question. But last time we used a substitution u equals something. And this time we have the substitution x equals 1 minus u squared. So same method, I've got my question here, I've got my substitution over there, and I'm going to start by differentiating it. The difference is I'll be finding dx, du. Now I'm not going to write down the du part down there. I'm just going to consider where it would be, and that's going to come over here. And differentiating here, I get negative 2u du. So that part's pretty straightforward. We've just got the letters around the other way. Now, looking at how we're going to use that, now we can see that dx can be swapped out for negative 2u du, so that's good. I've got something to use for that. And x equals, perfect. I've got something with u's in it that I can swap out for that, but I'm going to need something I can swap out for this part. So always look for your clues like that so that you can see what you need to do next. So rearranging this to see if it will help me, let's see if we can get it u equals in terms of x. We'll get the u as the subject. So adding u squared to both sides and subtracting x from both sides gives me that. So then if I say u is equal to, now here's the situation I was mentioning. We could be considering a plus and a minus here as our square root, but we're just going to use the positive square root this time to keep things simple. So now I can say, all right, this part here looks exactly like what I've got there. And then the last thing I've got to do is swap out my bounds. So there's a bit more work to do on the left. I'm going to say when x equals 0 and x equals 1, and then I'm going to do them one at a time so that I don't make a mistake. So let's do the 0 one first. When x is 0, I've got 1 minus 0, which is 1, and the square root of that is 1. So u equals 1. And when x equals 1, I've got 1 minus 1 there, so I've got 0. So hang on, one at a time. I said let's swap it out. So that's a 1. And then this one, which was here, is now a 0. Now I can just sub everything else in. I've got an x there, which is 1 minus u squared. I'll put that in brackets. And then for this part here, I just need u. And then for dx, I need minus 2u du. So I've got minus 2u du. Now these parts here have been multiplied. So putting them in brackets might help you see what you need to do there. Now on the next line, before we integrate, let's just tidy it up. Here I can see this is minus 2u squared, and I need to multiply that by both of the terms in here. So I'm going to get minus 2u squared when I multiply it by the 1, and then I'm going to get plus 2u to the 4, and then du. Now I'm ready to integrate because I've got two nice simple terms. So I can use my square brackets, raise the power by 1, and divide by the new power. Same over here, raise the power by 1, divide by the new power, And you'll notice that our bounds are the other way around now. It's almost running in reverse. That's okay. So subbing in the 0, I'm going to get negative 0 plus 0. And then I'm going to subtract. Now, you might be thinking, why am I putting that in? Strictly, you don't need to, but make sure that you don't make a sign error. If you leave out these two terms, you want to be careful you don't go straight in with subbing in the 1. You need to subtract the subbing in of the 1. So I've got a big minus sign there, and then brackets, and now subbing in, I've got 1 to the power of 3, that's just 1, so I'll get negative 2/3 plus 2/5. So we end up with the same answer as we did when we did it the other way around, 4/15. Different method, maybe slightly more complicated this way. There was a little more work to do, but it's just a good reminder that there's multiple substitutions that can help you to do the same question. This example uses trig, so we have to find this definite integral using this substitution. So I've set it out again the same, and I'm going to start by differentiating my substitution. So in this case, it would be dx d theta. And if I differentiate sine theta, I get cos theta, and I'm going to write my d theta over there. Now, that will help me swap out this part for all of that. I'm going to need to be able to swap out x squared. Well, that's straightforward. That will just be sine squared theta. And I'm going to have to be able to come up with an expression for this. Now, after doing a few of these, you're going to realize that when we're working with trig, we really commonly use those Pythagorean identities. Sine squared theta plus cos squared theta equals 1, or either of the other two that you can derive from those. So you can do as much of the working as you need to on the side. Some things you're going to figure out in your head, but it's really not a bad idea to just show how you got things that you put in over here. We'll also need to figure out our bounds. So if you can put everything you need here and then put it in, or you can just start working. I can see that on the top here, I'm going to have sine squared theta. So how about we just put that in? And I can see that my dx part is going to be cos theta d theta. So I've got that times that, and I've got that. I need to work out my bounds, and I need to work out something for the bottom. Now, quick inspection here tells me that if I've got x squared being this, then 1 minus x squared is 1 minus sine squared theta. Now, you might not need to write down either of those two lines. I'm just really spelling this out so I don't leave anyone behind. But now I can see that all of that is actually equal to cos squared theta. Now, again, this is my side working, so it's my space to set it out as I like. At this point, I could say, well, if I put a square root over this one, it's going to be over this, and it's going to be over this as well. So now I've got something that I can sub in for the bottom there. Now, I could sub it in exactly like that, or I could keep going and say, hey, I've got the square root of cos squared theta. That's just cos theta, isn't it? And by putting it in over here, it's really clear where I got it from when I sub it in on this side. All I've got to do now is find my bounds. So when x equals 0, what's theta? Well, when x equals, we can use this one. When x equals 0, sine theta will equal 0. So we're thinking sine of something is 0. There's multiple answers, 0, pi, 2 pi, 3 pi. In both directions, they go on forever. But let's pick the simplest one there, 0. And when x equals a half, theta equals, well, if x is a half, sine theta equals a half. And I know that there's many answers there for theta, but the simplest one is that the sine of 30 degrees equals a half, and 30 degrees is pi on 6. We'll stick with radians here because we're using integration, and whenever you're working with calculus, you need to work in radians. So now I've got this, we could go ahead and integrate, but we always want to make sure we're integrating something that's as tidy as we can get. So first thing we can do is tidy it up that way. Now, can we integrate sine squared theta? Have a think, how are you going to do it? And if you can't, don't despair, just think about how you're going to change it. You might need to rearrange the thing that you're trying to integrate a number of times before it's actually integrable. So the first thing I'm going to do is think, well, what can we change it to? We could change it to 1 minus cos squared theta. Will that help? Yes, it will. And again, my working on the side is helpful. 1 minus cos squared theta is the same thing as sine squared theta. So here I could just have my working. And that's the same as 1 minus, remember to integrate this, we've already seen that workaround, which is that we do half plus a half cos 2 theta. Sorry, it's getting a bit messy over there. So my working on the side, now I can tidy this up and say, well, what's 1 minus a half? That's going to be a half. And I've got negative half, so I need a minus there. And now I've got this. And now I can integrate that. So I've found a workaround and subbed it in. So now, let's have the equal signs here. We can use our square brackets. Integrating half with respect to theta, well, think what you would do if you're integrating 2 with respect to x. You'd say it's 2x. So if you're integrating 2 with respect to theta, you'd say it's 2 theta. So if you're integrating half, it's just a number with respect to theta. You're going to get half theta. So you could write that as theta over 2 or half theta. And then here, my method here, I reckon, is to say, well, I know it needs to be sine 2 theta. And now I can think about the signs. I need to differentiate this to make that. So sine 2 theta actually differentiates by bringing the 2 out the front. And then it changes from sine 2 theta to cos 2 theta. So I know that sine differentiates to cos, so this sign here will stay the same. Sorry, I'm using SINE and SIGN quite differently there. And now I need a term here that when I bring 2 out the front, it'll still make it a half. So I can see just by inspection there that I need it to be a quarter. And that's a way that you can, I suppose, work so that you don't need to integrate the 2 parts separately here and find a fixed factor. You can do it on the fly by just putting the part that you know will make it into the solution here, into the that you can integrate, and then differentiate this to check that it gets you back. And sure enough, 2 times negative a quarter is negative a half, and the sine 2 theta changes to cos 2 theta. So I've got it. Now I can put my bounds in and now sub away. So we've got pi on 6 divided by 2, that's going to be pi on 12, minus a quarter of sine of 2 lots of this. So the sine of, what's that, pi on 3, that's the sine of 60 degrees, which is root 3 on 2, minus, now when I sub 0 in here, I'm going to get 0, and the sine of 0 is also 0, so I'm going to get nothing but zeros there. So we've got pi on 12 minus root 3 on 8. Now some of the questions in this exercise are quite tricky, and where they get tricky is probably around about here, where you feel like you've done all the hard work and you've made your substitutions and the answer should just come out, and yet you're left with something that you can't actually integrate unless you change the form of it. So you just need to be persistent, have your reference sheet beside you to remind you of all of those identities and rules that you can use. Feel free to use your working on the side to throw something in that's equal to your integrand but is actually integrable.